Yeah, welcome back. So we have one more stream. So this time we will be working with uh, colored images, RGB images that will help us better understand how things working. Right? Okay. Um, okay. Okay. So let's get started. So basically, here in this session, we will be doing some simple things. That is to take an RGB image and classify them. Multi-class classification, right? So just to give you a brief, or just to show you the things that I'm using, the resources, right? I also wanted to show you this. So this is the book that I'm using, okay, and it's insanely good. They have just revised it for the PyTorch 2, even though the first version was pretty same, and the code is actually here in this repository. Please do go give them a star. It's really good, and you can go to the website also and see for yourself. There are a few other resources that you can follow. That is Daniel or Zero to Hero. Uh, PyTorch. So you can go in here, and this is basically a documentation of that whole course that is there. It's in Udemy. I think it's a brilliant book. It's a brilliant course, and he has also done more of a hacker's approach to the PyTorch. Daniel Brooks does not go through a lot of codes as such. I mean, a lot of theory, but more of a code approach. So he goes through how PyTorch works and also has an implementation of a paper, the VIT paper. I think that's beautiful. He has done crazy good work. All thanks to these guys who are making learning these things, self-studying these things so much easier. So these are the resources that I'm using. Okay. Um, Please do go shower some love on these people. I think this guy is coming with a new book. I probably will be buying this. Yeah. So cool. Okay. Cool. Yeah. So all I've done is take their examples, of course, and add my explanation into it, and maybe my insights into it. Also learning from them, and I am also debugging their code. Okay. So let's start with today's session. So we will be doing some rather simple things. What is happening here? Okay. Okay. Give me a second. Computer vision. Raw processor. Yes. Here we are. Okay. So what we are gonna do is right now classification of colored images. Secondly, we will learn about standardizations of these images. That is calculating some. I think we have gone through standardization or normalization. We have been through, right? So how do we actually do that if you have images, especially with multiple channels? And we're gonna train a model on that. We're gonna learn about dropout layers in more depth, what they are, how they work, and learn about how to find the learning rate to train a model, Adam optimizer. That is basically how to use the adaptive learning rates. We will capture the gradients and the parameter, visualize their evolution throughout the training, just like we did with hooks last time. We might also understand what momentum is, what nested of momentum is. That is basically a type of optimizer, which is we were using SGD. If I remember correctly, we will be upgrading ourselves to better optimizers. That is better, uh, yeah, better versions of gradient descents. And we will also know what how to schedule our learning rates so that we have different learning rates at the start of the training and the end of the training, right? All these things will be covered. Okay. Okay, so firstly, let's see our data set is basically this little guy here. This looks like this. rock, paper, and scissor. Our idea is to classify between these three. Okay. Uh, cool. So you have it installed. I have it here in a folder called RSV, and you can see the images here, right? All of them are here. So there's a one directory called RSP, that is rock, paper, scissor, and inside that you have three other folders like these guys. So basically it takes these folders inside the directory as their labels. Okay. So I'm gonna go through this code from here itself so that I can debug it as I go through it, right? Much easier for me. Oh my god, why is this popping up on the top? Okay. Again. Okay. Okay. Yeah. Here we go. So we have it downloaded. We are defining a composer, basically a transformation that you need to do on the image. We are resizing it into 28 by 28. Okay. First thing that we do is resize it. Cool. Why do we resize it? Because it's much easier on the GPU, right? Otherwise it's too big. So the data that we have is perfectly balanced, around 840 images per class. Okay, that is how it is, the data set that we have. And okay, the few things, like let's see that we are using image folder, that is Python's what do you say, PyTorch way of loading these images from the folder. There are a few parameters, you can read through it. Root is telling you or what folder all the samples are. Transform is telling you is there any transformation that you need to do to the images. You can also transform the target. So far that our target have always been integer, so this argument wouldn't make sense here. It start making sense if your target is also an image, like for a segmentation task, right? Segmentation is like you coloring regions in your images, right? Something like that. So and loader is a function that loads an image from a given path. In case you are using you are using weird or atypical format that cannot be handled by pill. So here also you can find the definition here. So a function that loads image from a given path. So if it cannot be handled by a pill, basically pill is another uh, library to do a lot of image stuff. Okay, and is validate to see is the files correct, as are they corrupted or something. You allow empty is basically telling you you can put uh, you can have this folder without any image inside it, but use that folder as a label something, right? So that can be done using allow empty. Okay, so all that stuff is here. Cool. Okay, that works. Hmm. So let's go to the code and let's see how the image looks like, right? This is our image. I'm gonna paste it here and let's see. You know what, let's do this in the notebook itself. So this is our temp data set. This is how it looks like. There are 2520 of these, right? And so basically 2000 2520 divided by 3, that is around 840 images for each class. Okay, so this is how the image looks like, one of the image. Okay, so this is 3 comma 28 comma 28 image, so it looks something like this. Okay, this is one image, how it would look like. This is a one image with three channels. This is a R channel, this is a B channel, R, G and B. Okay, so this is a three channels and every single channel has 28 by 28 numbers. Okay, and this is labeled as 0, so we are the first label, I think that it's rock. Okay, that label has been assigned to them. Cool. Cool. So this is the label and let's see. Now we are gonna go and just load it up, so it makes much easier instead of using a tensor data set that the classes that we create, to convert this in tensor or do any transformation right away. We are not using that, we are just using image folder at this point, and with that this data set can be used directly to be loaded as a data loader inside Python. So that is pretty cool, I feel, right? And let's go. I'm gonna reload this whole thing. Okay, keep the debug console on. Yeah, so this is how the image looks like. Now we're doing is basically we have a batch of 16. Okay, so this temp loader has 16 images in one batch. Okay, batch size is 16. So if I were to say, uh, I mean, there are 2520 of them, right? And I am saying it has every image, so it is around 158 of them would come in, if I am not mistaken. Yeah, 158 batches will be there, and every batch will have 16 images. Okay, there are multiple of these images. Right now, just think of this guy is having 16 image. Okay, so we are gonna go and do what we are going to do is standardize the whole data points, right? Using the normalize function. So before that, we have to find some statistics, that is the mean of and standard deviation of these data points, right? And how would you find a mean and standard deviation of an image, right? It's just pixels. So we're going to look into it, what it means and how to do it. So standardization, we learned the mean and the standard deviation. So what's the mean pixel for a rock paper scissors image, right? And what is the standard deviation of that? To compute this, we need to load the data. As is that so basically we have it in this loaded data set, right? It's a temporary data set. We will be using that in the temp loader. Cool. So so there's no need for a shuffle in this case because everything is perfectly aligned. Sorry, we don't need to bother with shuffling, as this is not the data loader we will be using to train our models. We will be using it just to compute the statistics. So by the way, we need statistics for each channels as required by the normalize transform. If you remember, the normalize uh, function required, give me a second, I can show you that. Normalize in PyTorch, right? TORCH. Okay, inputs, one of these, right? So you have this normalize, that is input. P is telling you what the exponent value dimension to be reduced. This has to be told which dimension it has to reduce. So all that thing we will need to tell, right? So this is the normalize, right? Normalize functional nature. I don't want the functional one, I want the normalized one. So I'll go here. Let's see if I can find the normalized one. There are many of them. Function normalization is there. It's a good thing that you actually go through documentation. It's always good. Um, Maybe I will go through the code itself once so that we can understand this. No worries. Okay, let me get it back here. Cool. Let's see. So basically we are talking about finding the statistics, right, of our images. So let's build a function that takes this mini batch of 16 images and the labels, and compute the mean pixel value and the standard deviation per channel of each image. So this is the image one. Okay, this is your one image. This is your one image right here itself. And so what you have here is, this is your image one. Let's say you want to find the mean values of all the pixels and the standard deviation of all the pixels here. That's for every channel. Okay, this one is happening. So this guy will have, so this R value, this is your R value, right? R image will have its own mean and standard deviation. G will have its own mean and standard deviation, and B will have, so red will have its own standard deviation and mean, green will have standard deviation and mean, blue will have standard deviation and mean, all that stuff. Okay, so we will be doing that. Cool. Let's load it. It's loaded. The function is initialized and function is added to the step-by-step class. And let's go to the function. So we have loaded our first instance of temp loader. That is our first 16 images, right? So if I can see the first image, it's right here. I'm just gonna do a shape on that just to show you the 16 images, and every image has three channels, R and G and B, and the pixel values are there, right? 28 by 28. Cool. I would also like to show you one of the image. Let's say I have this one and I'm showing you the shape of it. So this is one image. One image has, this is basically the first image, right? I'm indexing 0. So the first image with the channels being 3. So what I can do is I can actually see how it looks like. So if I do this and maybe increase this value, what you see here is this is your first channel. Okay, this is your first channel here. This is your red channel. I have given, let's say I have also shown it here. This is how it looks like actually. This is your red channel, this is your green, and this is your blue, RGB, right? I should also type RG, and this is the B. So R is there. So it's 28 by 28. So 28 by 20, that's what is here, right? 28 across the columns and 28 across the rows for the first. And then it's R, this is the G part. And this is the, oh my God, G part, and this is the B part. Okay. This is the B part here. So that is how that one image looks like. I want to find the mean of these guys, the first guy, right? So I have to do a lot of tensor operation that we learned in the first session, basically doing a mean and getting these dimensions, blah blah blah, all that stuff. So let's do that one by one. Okay, so this is your image. We are passing that image and the label. So you say image and the label is there. Label right now is all zeros, just so you know. If I put here, see, all of them are 0 because we don't care about them shuffling right now. We are not training it anyway. We're just trying to find the standard deviation and mean of them. Cool. It's gone inside. Okay, we are inside the function. Okay, statistics per channel, that's what we want to find. The parameters are image and the label. Now let's do this. The flattening of in a single dimension, basically this is the dimension that you have, right? The number of channels, number of samples, that is number of images, the number of channels, the height and the width, right? And I want to convert that into a single channel. So right now what happens is, if you do this reshape, we have already been through that. The -1 takes care of the dimension. That is, this 4D tensor is converted into a 3D tensor, where -1 tells them keep the first two dimensions the way it is, change the last two dimensions to fit the whole thing. So right now it looks, one of the image would look like 3 comma 28 comma 28. Now that image will be turned into, sorry, yeah, that's now the turn. If it was, let's say 16 comma 3 comma 28 comma 28, this whole will turn into 16 comma 3 comma 28 into 28, which is basically 16 comma 3 comma 784. Okay, if I am not mistaken. So 784, right? 28 and 28. Yeah, cool. And that is how it looks like. So one image now looks like, this is 16 images, right? If I were to say tell you, so the one image will look something like, it's a 3 comma 784. That is how it looks like. Cool. That is what we are doing. Flatten per image. Why it says flatten per image is simply, think of this whole thing. Now this visually how it would be like, I'm gonna remove these inside. Okay, this is your basically channels and stuff. Okay, that wasn't good. Okay, yeah. So you have these channels, right? This is your first channel, that's a R channel, and you have the pixels inside them. What we are doing is we are flattening it in a sense. We are taking, this is the first pixel, this second pixel, all the way to 28 pixel, right? And this is your, again, 29 pixel will be there. So if you are putting it in an array, it's 1 2 3 4 28 29 all the way till 784th pixel. All of them are flattened into a single line. So this R channel is now an vector, G channel is now an vector, and B channel is also now an vector. Okay, so this whole thing, this whole R is converted into a single vector. Basically, basically stacking all of them one by one. Okay, what do you call it, stacking or concatenating one of them. Okay, yeah. So now actually if I run this, I'm gonna do this, I'm gonna flatten it. So if I do the flatten and I do shape of that, it looks something like this. 16 of them, as I told you. And if one of the images, you want to know how one of the images looks like, it's the shape is this, and actual shape it looks like this. So this is your first channel, is your R channel, this is your B channel, this is your RGB channel, RGNP, right? So if you remember, uh, see this one, how it's ending and how this one is ending. 9961, this is also ending 9961 and 9922, that you see that. So basically this was your R channel, right, till here. So that is what I'm trying to say here. Cool. Okay, so now computing statistics for each image per channel, right? For every image per channel you have to average the pixel value per channel. So okay, all you have to do is take, now you have this one, right? You have this whole thing. If I were to show you, this is a long, there are 16 of them, but I'm just gonna deal with one image at this point. All I have to do is take the add all these up, right? I have to take the mean around that. So if I actually, I can also show you that here itself, right? If I take this and I say uh, I'm gonna run this once. Okay, this is gone. Now the mean is what? Yeah, you can see that mean is there, but we can do it here itself. So I am gonna do a sum on this, guys. Okay, if I do this, okay, that's sum of the whole thing. I'm gonna take the first index and do a sum of this, and then I am gonna take this guy and divide it by 784, and here we have it, 0.8765, which is exactly what we have here in the mean. If you say the mean, you see the means for the very first image, that is 0. First image for the first channel. So now how is this table represented is simply this is the first image, one row belongs to first one image. I hate this. One row belong to the one image. The first row, first column belongs to the first image, and the first channel, that is your red channel. Okay, I hope that makes sense here as you see that mean. Okay, so there are 16 of them. You can clearly see there are 16 of them here. Okay, that's how it's working. Now if I do the standard deviation, it's also, so how mean works is axis is 2. So what it tells it, for example, if I were to show you the size of this, so if you do the shape of this, it says I want to add, I want to mean over the 784 of them. So if I were to take like, just to recap how the axis works, so if I have the first image, right, this is your first image, I want to do mean, or mean on what I want to do. Axis would be here in this case, axis, sorry, axis would be actually 1, right, because the shape would be different. So you can clearly see this is what we get for the first image, right? This is how it works. So I hope that makes sense. For example, this is shape. You see the shape, I wanted to add all the 784 elements. So that's what it did. Add all the 784 element along the columns. So first axis is along the columns, right? Along the columns, go in all the columns and add all of them up. So you have first column added up, second column added up, third column added up. So that is what you get. This value is exactly what you see here on the first, for the first image at least, right? So for every image, it's gonna do the same thing. Cool. Standard deviation works the same way, right? I don't need to tell you how that works, and that we found. We now have this mean and standard deviation, just for our own satisfaction. Let's see how standard deviation looks like. This is how the standard deviation looks like. This is how the means look like. Both of them pretty self-explanatory. Should I increase the size a little bit? And if that helps, I don't think. Okay, that's enough. You have the standard deviation and also the mean for every channel of every image. Okay, that's important. So add up statistics of all images. All you have to do is then add all these things up, all of them up for red channels. Okay, so all I'm doing is taking the mean and I'm summing over the axis 0. So it will go along the row and add it up. So all I have to do is, if I were to show you, I'm just going to run this, right? I think pretty self-explanatory. And what you have is the addition of sum of means is simply this guy. So this is the addition of all these guys. All I have to do is mean dot sum, right? Sorry, means, I guess, means, right? This is the addition of everything. But if I put an axis on that, axis, axis equals to 0 along all the rows, and that's what we get here, and that's what we get here. Okay, cool. We added up everything. Okay, so I will sum up everything at the end of the whole thing. Okay, and now to make the tensor of shape 1 comma number of channels. So now you have basically, now this is done, right? So sorry, you have both of them. You want to take the number of samples and multiply it. What it does is, I think it's better to see rather than actually say it, with the number of samples. Make the tensor of shape 1 comma the number of channels. So it comes 1 comma 3, right? So it will be a one row with 3 columns, right? That's it. And we will be doing some stacking. That's it. It's much easier to understand that way. So if I were to show you this, what it looks like. Why is it opening by? I don't go. Okay. Oh my god, what is happening here? Want this? I don't want this either. Okay, yeah. So you can see it's 16 comma 16 comma 16. So what it did, it took this, that is 16, and it multiplied. So it's like multiplication of number of channels is 3. So it made it 3 times multiplication of our list. So this is something pretty cool, right? This is how it looks like actually. Yeah, you see that this is what it does. Okay, yeah, and we are putting it into a tensor. Okay, okay, cool. Now stack these 3 tensors on top of one another. So right now what we have is number of samples, the sum of the mean and sum of standard deviation, and we're just stacking it. Okay, we will see how it looks like. So if I stack this whole thing up, okay, I should have done something. Okay, no worries, we will do that. I'm gonna show you something actually before we do this. I'm gonna run this whole thing again. Okay, yeah, yeah, I was just need to reload it, but okay. So you have this, you got through this functions, and now after doing this, you have, right, this whole thing was done, if you remember. So the sum of means looked like this, and sum of standard deviation looked like this. Okay, yeah, and basically you are stacking all these things up. If I were to just take this and print it here, stacking it like this. So this is the, so basically the first column telling you number of samples. So there are 16 images, so there are 16 channels, right, or red, and there are 16 channels for green, there are 16 channels for blue. Okay, 16 images means, so let's plot, put it in words. Okay, so you had this image, right? You had one of these. Okay, what's happening? Okay. You had these images. Okay, that is a 3D image, right? You have R, G, and B, R, G, and B. Okay. Then there are 16 of them, so there are more of them, right? So same thing goes around here. R, G, and B. And so there are 16 of R, 16 of G, and 16 of B. Cool. I hope that works. And what we have done is we have taken all the pixels here, all of them, found the mean of, so basically these are numbers. We found the mean of it firstly. For this guy, we have found a mean, and for this guy, we have also found a standard deviation, right? And then what we did, we added all of them. This guy also. So this guy is also there. So let's say this guy is mu of 1r, and then this is mu of, sorry, not mu of, it's mu of sigma, standard deviation, sigma of 1r. This is mu of 2r, and this is mu sigma of 2r. So what we've done is essentially firstly done this mean, that is what we did here in the mean, and then we added them up here, right? You remember adding up the whole thing. So it's basically like adding up mu of 1r plus mu of 1 2r plus all the way till mu of 16r, right? So this is for your R channel. So this is your for R channel, right? R channel. This for same would be for G and B. G and B would have the same thing going on. G and B, right? Cool. So that's what we did. Okay. So the total mean. So the right now what we have here is, so did it happen for the standard deviation also? Okay. Standard deviation. Let's say I'm gonna call it mu like this, and this is standard deviation, and this is standard deviation of 1r plus 2r all the way, right? And so will be for this guy, and so will be for this guy, and this is mu and this is mu. Now what we have done is that function returns what? Firstly, it returns how many channels are there for R, G, and B. So this is your, let's say, R as your G, and this is your B, right? And I'm telling you that first telling you number of samples n. Okay, number of channels in the sense, and number of samples, they are same at this point. So and this one is telling you the mean of the whole thing, right? And this one is telling you the standard deviation of the whole thing. Okay, that's what we get here. So you have 13.8 and 3.05 and all that stuff, right? So this is what we get out of it, okay, for every channel. Cool. I guess that's a pretty deep explanation. Okay, I think we understood what it means, and let's see. So we just applied it for the first image, right? So we got the result above. For each column represent a channel, right? Every column is representing a channel, as you can see, and the rows are the number of data points, the sum of mean values and the sum of standard deviations. Cool. That works. Yeah, cool. Let's put this in the terms of the naming culture that we use. So this will be R of mu, and this will be R of standard deviation, G of mu, G of standard deviation, B of mu, B of standard deviation, right? Cool. This will just be n. Cool. That's fine. Yeah. So now let's we can leverage the loader apply method that we created in the first chapter to get a sum of the whole data set. If you remember, just go through the few of the first I think second or third sessions from the live stream. You will be able to find this. And Cool. So we're gonna do that. That's what we did here. Actually, we went through step by step. Apply loader. This is the data set, and we are applying this on all of it right now. Okay. So we are taking one by one, enumerating the loader. Loader is basically your data set, and we are taking the function that we have, function that we passed is the statistics function. We are stacking it up one by one. So let's do this. If the result is there, results. Okay, it's going through them. This is the first one. Okay, the first batch goes through it, and it gives out the results. So you can actually see the result is would be the same. The second batch coming in, and second batch is also done. So if I show you this results. Okay. Okay, I have to just say one more. Okay, now it will work. No? Oh, because it's not computed completely, right? So what I'm gonna do is I'm gonna just do this so that it computes the whole thing. Its length should be 158 because we found that there are 158 batches, right? So if I were to, okay, still calculating it. That's a pretty big calculations, right? So it's doing that. It's calculating basically. So by that time, what we are trying to do right now, if you understood, we did it for one batch, but we want it for all batch and then stack it up, add it up and stack it up, right? Cool. This is the result, and that looks crazy, but I don't think you need to go inside it. I will just show the results length. It's 158. Cool. So if you want to see, this is the first one. This is literally the first one that we had for the first batch, right? And this is the second batch. This is the third batch, and so on. Cool. That works. So now we are just appending, stacking all the results up one by one. Okay. Okay, cool. Let's stack it up. Stack them up. So you have this now, which looks like this. Before that, if you see the dimensions here, it was 2D dimensional, if you remember, right? But now as it's stacked, this became 3D. Stack adds one more dimension, if you remember from the few first classes that we had. Again, the length is of results will still remain the same. Cool, we stack them up. Now if the reduce is sum, in our situation it is sum, so we will just gonna be summing all of it. Results, we are adding everything. So let's see what it's adding. Okay, if you notice, the last one has eight samples only, last batch. Okay, so we are adding few things. What are we adding? We are adding along the first dimension. So if you see the results looks like this. We are adding for all the 158 batches. Okay, so if I were to add that, this dimension will be broken. Okay, so I'm not gonna do it in that. I'm gonna do it first here itself. If I do this, what happens? What it did, it went for all the batches, added everything up for that particular row and column. Okay, so this is 250 22520 is basically what your number of instances, right? That is what we want. This for this one, for first batch was 16. The whole of thing will be this much, right? And this is the addition of mean of all the images, okay, from every batch. That's what we did. I hope you understand what we essentially did at the end of the day. We took these 2520 images, we saw their pixels, okay, all of them, and we added them up to find the mean for, we added these guys up to find the mean, the ultimate mean, and then we also did all of them a standard deviation. So all the images, their means and standard deviations are being calculated. Let's do this, and that has been returned. So now the result looks like this. Results, this. Okay, I hope that makes sense. So we computed the average mean value and the average standard deviation per channel. Okay, still remember, this holds true. This thing holds true per channel. The R channel, what is the mean for the R channel is right here. That is what you see right here as well. Okay, better yet, it makes it a method that takes a data loader and returns an instance of normalize transformation. So all we have to do right now is create a function that does this normalization. So what it does is, now we have applied this loader over, this is basically the same function. The loader is uh, data set, and then the statistics per channel is there. And we got all stats here. Let's go through and one by one. So we are adding this method, and we are, give me a second. Okay, sorry for that. Yeah, so basically we were doing the normalization, right? So let's go through it once. um, so we have the total samples, total mean, and total standard deviation. That is a list of them. So basically this whole thing has been calculated. Oh my god, I should have done that. Okay, I was gonna calculate it. Okay, it's calculating it. Yeah, done. Okay, let's head over to, okay, so now so you, one by five, if you want to see total mean, so it will be the middle part. This part is the total mean of it, and the standard norm stand would be the other one. So all I have to do is take the mean of it with the total samples, right? All I have to do is whatever is the total mean and what is the total sample, that will be the mean of all the means. It sounds a little weird, but okay. So um, give me a second. So you have it there, mean of all the means, and you're passing that to the normalize. You're returning that function, right? And that is done. Let's see what normalizer looks like. Normalizer looks like with the, so you have this mean, okay, and standard deviation for every single channel. And now we can use this normalizer, right? This normalizer can be used to actually give you good answers, to normalize and stuff. Okay, okay, okay. Let's work with the real data set. We did that. We created everything. We have the composer. I'm gonna just skip through these parts. You have the training data set and the testing data set, or the validation data set, and you have a data loader for the validation. You are shuffling this time because we are making it ready for our what do you call, um, training purposes, right? So that's what we're gonna do. We will soon be doing some transformation, or we will also be seeing how it looks like the transformation on the actual image. So building a validation data set is also done. We are setting some seeds for reproducibility. Okay, cool. Yes, here I think we will have to go back to our here, yeah. Okay, we did those. I think I should run this guys once. Okay, it might take a little time, but okay. So we had this, we did run this. Now what you see here is first image and the first label. So right now what you see here is few of the images and how this compose and this normalizer has affected the images. I hope that makes sense. This is basically telling you how did our actual transformation takes place and how does it really look once you are done with the whole thing. Okay, I hope that makes sense. Run this so you can see clearly how it looks. So cool. So you might think, what the hell is wrong with this, right? There's nothing wrong with this, just the effect of standardization of pixel values. Now that we have this colored images, we can take the next step and use our convolutional, but this time a 3-channel convolution, right? So that's what we have with multiple channels. So let's go through it once, like how does the convolution over the multiple channels work, right? Um Here, I don't think you will need this one. I think it's pretty self-explanatory. I'm just gonna do this. Okay. So you have this image, right, with 3 channels, R and G and B. And you have this. So if your channel is 3, so you need a filter with 3 channels also. Okay. So before we start, we need to have, there are 3 channels for the image and 3 channels for the filters. So every filter has as many channels as the image it is convolving. I'm going to say it again. Every filter has as many channels as the image it is convolving. I hope that is fine, because if it somehow it was a 3-channel image, you will also have to have a 3-channel filter. Okay. So, but yet one filter, that is this, in this scenario, the red filter, I'm going to call it red filter. So red filter will convolve over the red channel and produce one output, a single valued output. Okay, that's what happening. This dude is convolving over this guy, and this dude is, sorry if I'm being a little, okay. So you see this, how it's happening. It's taking the first guy here and multiplying. Of course, 0 into 0 is 0, 1 into 1 is 1, 6 into 2 is 12, and then you add all these things up, right? 18, and so is for the green, and so is for the blue, and then again you add all this up to give you a one single value. So every channel, every filter will always give you one single value, and combination of all them will again give you one single value, and that is what we see for the first pixel here. I hope that makes sense. Let's go through one of the examples, right? So we are actually defining this whole thing, like this tensor, this tensor here. This tensor has been defined. Okay, you can see 508 and all that stuff is here. Run it once, and now this is a 3-channel filter. The filter is also, we are telling this is the filters, and that values are also being initialized right here. Okay, give me a second. Yeah, that values are also been initialized, right? And what else? And then we are going to use F to do a 2D convolution over it. We are passing in the region that is your images or regions RGB values, and this is your 3D channel filters. And as soon as we hit that, you get the value that we were expecting, that is the 39 value, and the shape of it is 1, 1, 1, 1. I hope that makes sense now. And that is what we got here also, 39, right? Cool. Okay. So this, now if we have multiple filters, right? If we have multiple filters, that is really cool. And now every filter will have one output, right? So this one filter number 1 has one output, filter number 2 has another output, and we just stack them up. So number of filters is telling you the number of outputs, if you really think about it. Okay, number of filters tells you the number of outputs. So if you have 2 filters, the input image has 3 channels. Each filter has 3 channels as well. The output has two channels. So number of filters tells you the number of. The convolution produces as many channels as there are filters. This is statement that is probably the most important of them, because we initialize thinking that, for example, the input and the output. The input we put is the number of channels that our image has, but the output is the number of filters that we have, right? And the number of, so the convolution produces as many channels as there are filters. So this filters, number of filters that we pass, produces as many channels in the output. So if we had 10 filters here, it will be a stack of 10 images filtered, right? So that would be the channel part here. Here instead of 2, it will be 10 here. 1 into 10 comma 4 into 4, right? Okay, that's what we see. Now I hope 3D part is done. So basically working with 3 colors or the multiple channels is understood. Now we can work with basically working with that part is done. So build a much fancier model, right? Instead of using sequence, what we can do is we can actually, this is how most of the code you find on PyTorch looks like. Okay, they're pretty simple. So let's leave the sequential model aside and let's build a model class again. This time our constructor method will take 2 arguments. This is a constructor method and taking 2 arguments, that is number of features, and one value called p, and p is something that we will come across a lot, and this is basically a value for our dropout, probability for our dropout. So we will get to it. We will use number of filters as the number of output channels for both convolution blocks or our model. Yes, there are 2 now. Okay, so as we can see from the code, we will be using a p for the probability of dropout. Okay, so let's define it. So you will go through it one by one. So we have the first line. This is a constructor. We have initialized 2 variables. We are using this as the super is used to get this is constructed from this module nn dot module, right? And you are initializing the features, then creating the convolution layer. This time we have 2 of them. The first convolution layer has three channels as the input because there's an image with three colors, right? And the output is the number of features that you want, or the number of features you want, or number of filters you want, and the kernel size is 3 by 3. And whatever is coming out of this guy, I want them as the input for the next convolution layer. And then I want the same as the output also. There are two of them. Okay, so now we will create a linear layer. So here is NN, and why is this 5 into 5? We will get to see that. And we want the input to be this shaped, and then the output is 550 and 50 goes to 3. So finally it looks like there are 3 outputs. Okay, now the featureizer. So now here is all the thing that has been passed into it. Okay, we'll go through it once. The first is there are 3 channels, and the shape is 28 by 28. After going to the first layer, so it going to the convolution layer number 1, what it happens is the first convolution layer will just make it 26 into 26. You can calculate that from the formula that we have seen, right? And then due to max pooling, this whole thing becomes half. Okay, that's happening. In the second convolution layer, we are taking the same features, right? And then passing, and it's become 11 and 11, and because of max pooling, that again becomes half. So it's taking the floor of the whole thing, right? That part is done. So that's why you must have seen this 5 by 5 here. It actually comes because after passing through these 2 blocks of convolution, the feature looks like this. The shape of the image is 5 by 5. So we want this whole thing to be in the start of the linear layer, right? So you have this. So the input dimension is this. So the output dimension should look like this, right? So you're flattening everything. Once you flatten the whole thing, you have one array, and that can be passed through a single linear layer, right? So you have the classifier layer here. If the p is greater than 0, we apply the self. In this case, actually we have okay, default is 0, so it won't go there, but start from here. Okay, just so you know, you must have seen the x is used as the input. X is basically your input, and one by one it's going. First here, as you know, the operation goes from right to left. So first this thing happen, first these thing happen, and then it goes to the next part. It assigns to the x, then again this part, then assigned to the x over and over again, and then the x is returned. Now again that x is taken up, and you can see here in the forward part is there. First the featureizer is, then the classifier. The classifier is what we are trying to do now. So this is taken up, we are passing it to the layer and the ReLU, and now the input is 50, and then again for the last one we are assigning this dropouts if it's there after every single layer. We'll get to that. Okay, so that is how the whole thing looks like. Cool. So few insights is there are 2 convolution layers firstly, and 2 linear layers, f1 and f2. So there are 2 convolution layers and 2 linear layers. Where are the layers for activation function and max pooling? Well, max pooling layer doesn't learn anything, so we can just use a functional that is fprot. That's what we are doing. It's not learning anything anyways, so you can just do, it's just an operation on the on those tensors, right? So we can just use f in that sense. Okay, same goes for ReLU, right? If you choose to use, like, there's another what do you say, activation function that we have discussed, is parametric ReLU, then you shouldn't be using the functional form, since it is need to learn the coefficient of leakage, basically the negative part. If you remember from the lecture on activation, is basically this guy. This is how the ReLU looks like. I'm gonna draw ReLU with green. Let's say ReLU looks like this, right? But parametric ReLU, what it has is some kind of a parameter, let's say alpha, and instead of this it goes like, let's say this one, it goes like this, some parameters, the slope for the negative part. Okay, so this part is defined by this parameter. This is also learnable. You can put it as a learnable. In that case, you cannot use the F part. Okay, cool. um, how long has it been? Okay, it's already 1 hour. Is that so? Yeah, it's okay. mm, cool. So on one hand, you keep the model's attribute to a minimum. On the other hand, you don't have layers to hook anymore because you're not using sequence, right? You cannot do the hooking, so you cannot capture the input of output of the activation function and the max pooling operation anymore because we are building the model. If we had used the sequence, then sequential module, it would have been I mean, we could have been able to actually visualize through hooks. Okay. Okay, cool. So now, I hope this architecture is kind of understandable. And okay, so next part is about dropouts and how they work, why they work, and I guess we should drop this right now and start dropouts in the next session. Okay, thank you for joining in.